Hi everyone, I'm Simone Masocco, a PhD student at the Department of Geosciences of the University of Padova, and I study faults. In particular, I study fault architecture or geometry. This because fault architecture is one of the factors that control earthquake nucleation and propagation. And I'm a field geologist, and what I do is mapping fault rock distribution and fault fracture network distribution across a fault zone. This because through geophysical observation or drilling project, we don't have a very high resolution imaging, we say, of the fault architecture as seismogenic depth. So I mean between 5 and 15 kilometer depth in the continental crust, where most of the continental earthquakes nucleate, for instance, magnitude 5, magnitude 6 or 7. And the continental crust is where most of the human activity occur, or where we live. What I'm going to talk today is a study of a fault zone very well exposed in the Atacama Desert. And what we did is to map the fault architecture along strikes, so in different places along several kilometers from one to another one, to describe the architectural variability of these faults. And we were so interested in this fault for two reasons mainly. The first one is because the fault is very well exposed in the Atacama Desert, because there is no vegetation, because it's a desert. And the second one is because we found pseudotectilites, so this black stuff here in this case, and these are the result of frictional melting during an earthquake. So we know that this rock was generated during an earthquake, and so we can prove that this fault were capable to generate an earthquake million and millions of years ago. So in this study, we describe across a scale the architecture of a fault zone, and what we found is that we found pseudotectilite, first of all, so this and based on the dimension of the fault, this fault were capable to generate a magnitude 6 or magnitude 7. And the second interesting point is that we found a network of veins, like this layer, green layer here, that based on mineralogical and microstratigraphic observation, we could say that this vein precipitate a condition of from a knot fluids. So that those are the conditions at which continental earthquake nucleates, because there are a lot of fluids in the crust, especially at that level. And so based on the scale of microstructural and mesoscale observation, we could compare this fault vein network with current with a particular kind of seismicity that is called earthquake swarm activity, that are not a classical main shock aftershock sequence, but is related to a widespread and a continuous earthquake sequence with very small events that can last from few days to a couple of weeks and is fluid driven. And this is so interesting nowadays because we do a lot of geothermics or CO2 storage at depth, and we could use our exhumed analog to compare, to know what's going on when we do geothermal exploration or CO2 storage, or in case this can have application on safety. Because when we pump fluid at that, we could reactivate a fault, and we can have somehow an understanding from the geological point of view what's going on when we do this kind of operation.